This is the video demonstration of the project Local Binary Convolution Neural Network. Basically, the main idea of this project is to show that we can reduce the computational complexity of the CNN by using local binary pattern without losing on performance. We will implement a 6-layer deep LBCNN and then train it on standard data set, which is MNIST dataset for our case. Then we will show that with reduced number of trainable parameters, we can attain acceptable accuracy for the model. Let's first see what the overall model architecture is. So in this architecture, the model is 6 layer deep, and you can see here that each block represents a layer, and we call it like local binary convolutional unit, and there are 6 of them. 5 of them are the exact LBCU, and the 6th layer is the fully connected units. So each layer having different number of filters, like this is having 8 filters, 16, 32 and so on. This is the input image, which would be a 28 by 28 grayscale image having the numbers 0 to 9, and the true class for that will be the same labels 0 to 9, which is the exact form of the MNIST dataset. So let's see what is within the units. So each LBCU units contain all of these, where the input image will be coming from outside. Then there are filters. There are two specific things to mention about filters. First one is the weight related to these filters are non-trainable, which is the special feature for LBCM, because of these non-trainable weights we are going to reduce the parameters. And the second thing I want to mention about these filters are they all are binary filters, and we have created it with a specific value of the sphericity, where sphericity refers to the number of non-zero element. Like here sphericity is 2, which means like there are 2 non-zero values and all other values are zeros. So do the sphericity is increasing, and so do the non-zero values are increasing, as you can see from left to right. So now directly this is the things for the filters, and what happens is like image will be having the convolution with these filters, and then we have the difference map which will be fed to ReLU unit, and ReLU unit will give exact binarization, and it will give zeros and ones in the bitmap. So these are the only trainable weights, which would be 1 by 1 weights, and the dimension would be depending upon the dimension of the bitmap, the depth. So it will be convolving with the bitmap, and you will be having the feature map as the output, which will be fed to the second layer. So if this is the first layer, this would be the input image, and this would be the output, which would be the input for the second layer. So the hyperparameters for these are the 8 units. Like here the filters are 8. So in the first layer we have the 8 filters here, and in the second we have 16 of them, then 32, then 64, then 128. Then after that we will be flatten out the output and give a fully connected layer, and which will give an output. So this is about the architecture and all the details regarding the parameters, and what are the hyperparameters we are using, the learning rate, optimization options, loss function, padding, stride, already is included in the report. So let's move to see the platform. So we will be implementing the whole structure on a newer platform called Jupyter Notebook. So we will be calling the Jupyter Notebook from our command prompt, and it is an interactive tool which is an web application. So we will be creating all the implementation part on this, and here you can see that it will give you all the details, like which are the files available. So I have created in the test, and here the files are created as IPYNB, that is the IPython shorter form. So this will be our code, and you will be seeing that the various steps of implementation, like we will be firstly having all the imports. Here we having all the imports, then we will be having the dimension of the data. We mentioned like it is a 20 by 28 the image input size, the number of channels and all that. Then we have the placeholders variables, which will be including all the placeholder, uh, like for the TensorFlow we will be implementing it with the TensorFlow library, so it give you all the details about the TensorFlow. Then we will be loading the data set, and it will load the data set here, and because the files we have to unzip the file, so we use the gzip here, and then we load it to the specific specific arrays, that is dataset image, data test labels. So after that we firstly see like the data set, so that we are confirmed that it's been loaded correctly. So here you can see the trainable sets is 60,000 and a test set is 10,000, and with the help of plot image we will be plotting some of the data sets to confirm that it is correct. So here you can see the image set in a shorter version. So here you see the true label is the 7, and the image is this, which is also 7. So it means that the data is loaded correctly. And now we will like I mentioned earlier, I will be uh, passing some variables like the height, width, then filters in the first layer, the filters in the second layer. These are the height and width of the filters. So for the all the 6 layers I define here. Then we will be having the special new LBC layer, where you can see that where the difference is, like in the standard TensorFlow, if you're creating the binary network, sorry, the neural network, you are just creating it by means of convolution command, this command. But here you have the filters, which are binary filters. So firstly we will be creating the binary filter weights, then we will be having calling the the second one, the difference matrix, that is so firstly we will be having creating the for every LBC layer we will be creating the weights for the filters, then we will be creating the difference map. So here you can see that we created the new LBC layer. We pass all the parameters here, then we created the non-trainable filters with the help of the new weight non-trainable function, which is written below that. Then there is a difference map, and that will create if you every detail is written in the comments, so if you're having any doubt you can go through that. So it will create a new LBC layer. So do it creates the weights, biases, then creates the convolution, the variables, all that. And finally let's go to the result section, because we have a limited time here. So in the result section, what I do is I made an iteration of around 6,000 iteration, because it's a batch process. So whenever I fix the batch numbers for the trainable, that is 128 data set at the same time, and then the parameters are optimizing for that, then we will be having the another batch which is selected randomly. So here you can see we have an iteration. So here you can see the first iteration there was a just training accuracy of 18%, and it is increasing very fastly and rapidly, 85, 94, 97, 92, 96, and so do I make like 6,000 of them. So we have like 6,101 optimizing iterations. So then I give a keyboard interrupt to stop, because initially I have put them like 10,000 count, but it taking too long because I am making a 10,000 of command here. So then I interrupt it in between, and then I calculated the test the accuracy on the test set, and it gave a very good number of the 98.3% test accuracy, which is a very good test accuracy for this short amount of iterations. If you increase the iteration amount to like 20,000, 30,000, surely it's going to boost above 99%. And this is regarding the code, and let's go to the result section to see what we are trying to prove. So here you can see that with this model you can have an comparable accuracy with the neural networks, but the convolutional neural networks, but you can see that we have reduced the parameters, because if you implement the full structure here with the standard convolution network, the same architecture of 6 layer, it would be like 1,23,080 parameters, trainable parameters, but we have trained it just for 56,832 parameters, which is a kind of like 53.82% drop in the trainable parameters. So thus we can say that we have reduced the computational complexity of the model of CNN by using the local binary pattern, and we having the comparable accuracy, like 98.3% accuracy on that, which is a quite good accuracy. And surely if we are going to increase the number of optimization iterations here, so if we are going to increase this number of optimization iterations, then we are surely going to increase the number of the accuracy kind to above the 99%. So thus at the end I just want to say the future perspective of this project is to just because we implemented on the MNIST data, there are a lot of other data sets you can implement on that. And the second thing is because we have implemented just a 6-layer deep data set, 6-layer deep neural network, you can increase the depth and use other standard like networks to implement it to see the results. But with this 6-layer depth of layer, 6-layer deep network, we have having a quite good results. So if you are having any doubt, you can ask me anytime. Thank you for your time. Have a nice day. Bye bye.